Good morning. Today we're going to talk about designing Iir filters. First we're going to do Iir filters, then we're going to do FIR filters. The thing is, for many years people have been designing filters. Of course, there have been analog filters. Before people started using DSP, they used analog filters. And all of those analog filters were Iir filters. And so we have a large body of knowledge of how to design Iir filters. So one of the methods for designing these digital filters is to design an analog filter and then change it into a digital filter. And that's what we're going to do here. How to change it, we're going to talk about later. Today, we're only going to talk about how to design an analog filter. So, when we design the analog filter, of course, the first thing we always do, is start with the specifications. Let's start with low-pass filters. And so the specifications that we're going to have are going to look something like this. Now, this is an analog filter, so the axis is now radians per second. And we're going to use capital omega for the frequencies. So we have a pass band from 0 to omega p, a transition band, and then a stop band from omega s on. And the same magnitudes that we had talked about in the last video are the ones we're going to use for the specifications. Now we're going to start off looking at Butterworth filters. Some semesters I talk only Butterworth filters. Some semesters I talk about some of the other filters. This semester we'll probably only do Butterworth filters. The thing is, once you have an idea of how to design a Butterworth filter, designing the other ones is similar enough that you could just go to a book and look it up if you need another type of filter. Now, Butterworth low-pass filters have this property. The magnitude squared of the filter is going to look like this. Of course, since it's the magnitude squared, right, it's the transfer function and multiplied by its complex conjugate. And it's going to look like this, where k is a constant, omega c is the cutoff frequency, and n is the filter order, right, 1, 2, 3, 4, and k is the gain. Now, the k that we're using here and the k that we're using in the specifications are not necessarily the same. It turns out that we can use them to be the same and it simplifies it, but they don't have to be the same. Now, what does this look like? If we were to take this, of course we have a magnitude squared, so there's no phase. The magnitude squared, what would it look like with omega? Well, immediately see that if omega is 0, this is just k. So when omega is 0, this starts out at k. This should be k squared, sorry. There we go. So when we have omega equal to 0, the magnitude is going to be k squared. And as omega increases, this is just going to decrease, right? It's what we call monotonically decreasing. As omega increases, this fraction is going to decrease, always. When omega is omega c, right, this term would be 2, this term would be 1, so it would be k squared over 2. And that would be the magnitude squared. If we just took the magnitude, well, it would look very similar, except it would be the square root. This would be k instead of k squared. Here we would have k over square root of 2. Now, this difference is a difference of 1 over square root of 2. And if we look at that in terms of decibels, dB, right, 20 log base 10 of the difference in voltage level, then this would be the same as 3 dB. And so the cutoff frequency for our filter is the frequency where the magnitude is down by 3 dB. And this is a common specification. As I had mentioned, Butterworth filters are monotonically decreasing, right? This always goes down, it never comes back up. So if omega 1 is less than omega 2, right, this magnitude here is going to be greater than this magnitude here. And we're going to use this property later on when we're designing the filter. Now, to meet the specifications, right, to meet the specifications, what it means is this line has to be inside this area here. So it means, right, from in the pass band, from 0 to omega p, the magnitude squared has to be between k squared over 1 plus epsilon squared and k squared. In the stop band, for omega greater than omega s, then the magnitude squared has to be less than k squared over a squared. And here we're using the magnitude squared for the specifications and the magnitude of the transfer function. In other words, this is what it has to look like. Now, we know that this function, the magnitude, is monotonically decreasing. What this means is the following. If we look at this graph here, if the filter meets the specification at 0, and if it meets the specification at omega p, it's going to meet it for all the frequencies between, because since it only decreases, this would be the maximum point, and this would be the minimum point in the range of frequencies from 0 to omega p. So in other words, this is the maximum value. This would be the minimum value in the pass band. And so all I need is for the maximum to be less than k squared and for the minimum to be greater than or equal to k squared or 1 over 1 plus epsilon squared. To meet the specifications for the stop band, I can see that the biggest value in the stop band is right at omega s. If omega s, we meet the specifications, in other words, if at omega s the value of the filter is less than what we want it to be, then it's going to be less for all other frequencies. It's never going to go up, it's always going to go down. So if we meet it for the greatest value, it's going to be met, the specifications are going to be met for all the frequencies. And so we have 3 inequalities here. And so we can use these 3 inequalities to get the 3 unknowns from our filter. The 3 unknowns are k, omega c, the cutoff frequency, and the filter order n. Let's start off with this one, right? We start off with the first one. Let's say we want this to be less than or equal to k squared. Now, we know that the magnitude squared of the filter at omega equal to 0, let's look up here, is just going to be k squared over 1. And that we want it to be less than or equal to k squared of the specifications. And of course, as I write here, this is the k of the filter, this is the k of the specifications. And although they don't have to be the same, we can generally, just to simplify things, make them the same. And of course, this is going to be met always. For the pass band, we substitute omega for omega p, and we want this to be greater than or equal to k squared over 1 plus epsilon squared. Now, if we make the k's the same, then they will cancel out, and this is the equation that we get. Now we look at this and we go, okay, we can simplify this a little bit, right? We can multiply both sides, we can get rid of the 1's, and this is the equation that we have. Epsilon squared greater than this fraction of frequencies. The last inequality, if we substitute omega equal to omega s, this is what we get for the magnitude squared. And we want this to be less than or equal to k squared over a squared to meet the specifications. Again, if we cancel k squared, then we get this, or we get this equation, or moving this over to the other side, we finally end up with this. Now, let's combine these 2 equations. Let's combine this and this. Let's make a division. Okay. So we know that this has to be greater than or equal to this. This has to be greater than or equal to this. And in the denominator, this has to be less than this. And we do that so that we can cancel out one of the unknowns, right? Omega c is unknown, we cancel that out. And in this equation, the only unknown is n, right? We know from the specifications omega s and omega p, we know from the specifications a and epsilon. So the only unknown in this equation is n, and so we're going to find the equation for n. And if we do that, we simplify it. And this is the equation that we get for n. We see that n, which is the order of the filter, has to be greater than or equal to this number here. And all of these numbers, again, we get from the specifications of our filter. Now, n has to be an integer. The order of our filter has to be an integer, right? Order 1, 2, 3, 4, etc. And so this number here is generally going to be some real number, generally not an integer, right? So if it gives us 2.3, if this number gives us 2.3, n would have to be at any integer greater than 2.3. So it would be 3 or 4 or 5 or 6 or any on. Generally, we don't want to use an order greater than necessary. If we meet the specifications, good. And so we just usually use the smallest integer greater than this number here. Now, once we have n, or once we have chosen n, we can go back to the other equations and find omega c, right? So from this equation, here the only unknown would be omega c, and so if we solve for omega c, this would be the equation. In the other equation, we also have omega c. In solving for that, we have this equation. And so combining these two equations, which are inequalities for omega c, we now get a range of frequencies of omega c. So combining these two, we see that omega c has to be between these two limits. We could have omega c be equal to 1 or the other limits, or any number in between. So the idea was this, and what does it mean? Now, if we have omega c equal to the lower limit, when we make our filter, we'd get something like this. In this case, since we've chosen the k of the specifications to be the same as the k of the filter is always going to touch at this point. If omega c is equal to this, it means that it's going to touch at this point omega p also. And then at this frequency, it's going to be a little less than the specifications. If we go with the high inequality, if we use the higher value of the inequality, then it's not going to touch here, but it's going to touch at the frequency omega s. And so here it's going to be a little better than the specifications, and it's going to just meet the specifications at this frequency. Once we have k, omega c, and n, of course now we can get the transfer function. This is the function that we need for the actual filter. What we saw before is the magnitude squared is equal to this function. Now, since we have it written in h of j omega, the complex conjugate will be changing j for minus j, and so this is what it would look like. Now, we want to get the transfer function, which is of course a function of s. So we can substitute here, and we can get the same function, but now in terms of s, to be able to get the transfer function. And when we look at this, of course, this is the multiplication of two transfer functions. We see it has order of 2n, right? The denominator is a polynomial of order 2n, so it has 2n roots, and so this multiplication has 2n poles, right? Half of the poles are going to be for h of a, and the other half of the poles are going to be for h of a of minus s. Instead of going through a long derivation of where the poles are, let me just give the formula. This is where the poles are. Instead of memorizing this, it's easier actually just to think about it graphically. It turns out that the poles are equally spaced around a circle of radius omega c, symmetric with respect to the j omega axis, and no poles on the j omega axis, on the omega axis. So for example, if n is equal to 3, that means we're going to design a filter of order 3. It would mean that 2n is going to be 6, and so there are 6 poles on a circle with the radius omega c. Now they're equally spaced around the circle. If the circle, right, has 360 degrees, if there are 6 poles, 360 divided by 6, it's going to mean there's 60 degrees between each of these poles. They're going to be 60 degrees around. Right, for if n is equal to 4, 360 divided by 8 would be the spacing of the poles. Now, they're going to be symmetric. Half are going to be in the left half plane, half are going to be in the right half plane, and there are no poles on the j omega axis. Right, so like this pole, the negative of this pole is going to be over here, so this would be a pole that we want for h of a. This would be the corresponding pole for h of a of minus s, and the same way for the other poles. And so each of these poles has a corresponding negative on the other side. One pole for h of a of s, the other pole for h of a of minus s. Now, of course, we want a causal stable system, so we choose the poles in the left half plane for h of a of s. And so, for example, in this case we would choose p of 0, 1, and 2. Here we would choose p of 0, 1, 2, and 3. So we're going to go from 0 to n minus 1 for the poles of h of a of s. And this is what our transfer function is going to look like. The poles multiplied by a constant factor k, the same constant factor k that we got, and the cutoff frequency. If we multiply this out, instead of having it factored into poles, if we multiply it and get the polynomial, right, we're going to see it's a polynomial of order n. And if we divide by omega c, this is what we get. This would be the function that we get. And if, of course, if we multiply this by h of a of minus s, then would get, right, this function to the minus, to the 2n, and the other terms would all cancel out. So this is what our transfer function is going to look like. And we already know what k is, we know what omega c is, and we know what n is. What we have to calculate now are these coefficients a1, a2, a3 to a of n. We know that the last one is going to be always equal to 1. Now, the easiest way to do this is not to use this polynomial. It's actually easier to use this one, right? So or in other words, we're going to calculate what the constants, the a constants are, assuming that omega c is equal to 1. So we're going to calculate the pole locations assuming omega c is equal to 1. So in other words, in this graph, omega c we're going to choose equal to 1. We find the a's, right? So we find where the poles are. Once we know where the poles are, we multiply them through and would get this function here. And then, right, that would give us the constant a's, and then we can multiply by omega c to get the final polynomial. Now, let's go through an example to see how this works. Let's say that we have n equal to 2, right, we're going to choose omega c equal to 1. And so we have 4 poles, right, 2 poles for h of a, 2 poles for h of a of minus s. Now, where are these poles? Well, I know that the 360 degrees are divided equally between the 4 poles. And so there's going to be 90 degrees between each of these poles. Now, since there's no pole on the j omega axis, and they're symmetric on either side of the axis, right, so it means that this is 90 degrees, this is going to be 90 degrees, so this would be half of 90 degrees, so this is 35, this is 45, and this is 90, which would give us 135 degrees. Right, so P0 is going to be the value with magnitude 1 and angle 135 degrees. And we can write that as, right, minus 1 over square root of 2 plus j 1 over square root of 2. P1 is going to be the same thing, except, right, also on the radius, on the circle of radius 1, but it's going to be 90 degrees more, so it's going to have an angle of 225, which would give us minus 1 over square root of 2 minus j 1 over square root of 2. Now, when we substitute that into our polynomial function, s minus p0 and s minus p1, and remember here it's minus, we substitute it in, we multiply this out, and this is what we get. So we'd get s squared plus square root of 2s plus 1, and so this would be our constant. If omega c is not equal to 1, then we'd have to multiply by omega c to get our final transfer function. Now let's go through a complete design of a filter now. Let's say these are our specifications. Specifications are always going to be given in dB. So in the pass band, we want the magnitude to be between 3 and 1 dB. And then we want at least 10 dB of attenuation in the stop band, 300 pi radians per second more. The first thing we do, because the specifications we had used to design the filter are not dB, we have to convert from these values into non-dB values. So, right, 3 dB is equal to what? Right, 20 log base 10 of something is going to be 3 dB, and that something, of course, is 1.4. So we do the same thing for 3 and 1 and minus 10, and we get the non-dB values. And so these would be our specifications in non-dB values. And these three numbers are the numbers we're going to use for our design, right? This would be what we would call K. This was K over 1 plus square root of 1 plus epsilon squared, and this would be K over A. And so we just equal these things out. We can solve for K, we can solve for epsilon squared, and we can solve for A in that case. Once we have those numbers, of course, then we can immediately go back. We're not going to derive our formulas again. We know what our formulas are. For example, the formula for n was this thing here. So we substitute what A is and what epsilon is and what omega s and omega p are. We get this and we get 1.58. This doesn't need to be great precision, right? Because we're going to get an integer value from this. Since we get 1.58, we're going to choose the smallest integer value greater than this. And so we're going to choose n equal to 2. Once we have n, then we can go and find omega c with our other formulas, right? We substitute epsilon squared, we substitute n, we substitute a, and this is the equation we get. So we solve for these two numbers, and we find that omega c has to be between these two numbers here. Now it can actually be any number at all. Just for simplicity, because this is a problem in a notebook, right? I'm going to choose some nice round value, right? It has to be between 114 and 143. So, right, 120 pi, 130 pi, 140 pi would be numbers I would probably choose to do this problem on paper. So then we go back. We have to find the poles. Now the poles we just calculated, so I'm not going to calculate that again. So we find the poles assuming omega c is equal to 1. We know that this is the value that we get substituting what k is. Now we know that omega c is not equal to 1. So we have to substitute that here in our formula. We put what omega c is, and this would be our final value for a transfer function. This is a low-pass Butterworth filter of order 2 with a cutoff frequency, right, of 120 pi radians per second, in other words 60 hertz. Now, I had mentioned that sometimes in other semesters I look at we design other type of filters besides Butterworth filters. This semester we probably won't, but let me go over the general idea. Now, as I write here, there are other filter types. The most common, Chebyshev type 1, Chebyshev type 2, and what we call elliptical filters. Now, what do these look like? Now, we just looked at the Butterworth filter. The Butterworth filter is what we call maximally flat, right? A low-pass filter is going to look like this. Now, of course, what we want in a low-pass filter is to pass the low frequencies and to cut the high frequencies. So the faster, the sharper this cuts off, the better it is. It turns out that the Butterworth filter is the polynomial that has the sharpest cutoff without ripple, right? This is monotonically decreasing. There's no up and down here in the magnitude of the transfer function. Now, Chebyshev type 1 has ripple in the passband. The cutoff is faster than in the Butterworth filter, so it goes down faster than here, but it has ripple in the passband. As you can imagine, Chebyshev type 2 is very similar, except it doesn't have ripple in the passband, it has ripple in the stopband. And so again, it goes faster, it cuts down faster, but it has some ripple in the passband. If we don't mind the ripple, well, great, we can use this type of filter. If we don't want ripple, then we'd have to use something like a Butterworth. And then finally, the elliptical filter, as you can imagine, is the one that cuts off the fastest, but it has ripple in both the passband and in the stopband. So there's a trade-off here between ripples and cutoff, right? The more ripples, the sharper the cutoff. There's some homework problems I want you to do. This is basically what we did above. So you're going to design the analog filter for the following specifications. Redo the problem for this, and this, and this. The order of the Butterworth filter. In this case, I don't want you to design the filter. I just want you to find the order of the filter. This are more realistic specifications. These specifications are kind of simple so that the order isn't too high, so that the design is not too difficult. But if you're going to actually have to manufacture something, I believe these come from a specification in a digital to analog converter. I went in and found the specifications of the filter that they use, and it's actually these. And so this comes from an actual component. So having 90 dB of attenuation, 0.1 dB of ripple in the passband. This comes from an actual product. And so I want you to find the order of the filter for this case. Don't find the filter, because if the order is large, finding H of A is complicated, but find the order of the filter.